Hi friends, in this video I will discuss about scan insertion interview questions. First, what is scan insertion? So it is a very important question. So interviews may be asked this question, what is meant by scan insertion? Converting all normal D flip-flops into scan D flip-flops by inserting 2x1 mux. So 2x1 multiplexer is a universal solution for the converting all the normal flops into scan D flip-flops. So after converting scan flip-flops, so we need to stitch the scan flaps into scan chain. So that is Q to SI path. So in scan chain we will have Q to SI path. So in this figure you can see about what is, so this is a regular flap or normal flap. So here we are inserting the mux. So by that we are converting into normal flaps into scan flaps. So here so we'll get extra connections like scan input, scan enable and scan out. So these three extra pins we will get after converting normal flap into scan flap. So next one, explain scan chain operation. So scan chain operation mainly depends upon the scan enable. So when scan enable is equal to 1, so shifting operation, so data will be shift one flap to another flaps. Okay. So while shifting operation, so clock pulses, number of clock pulses is equal to number of flip flops. This is very important. So when scan shifting, so how many clock pulses are required? So clock pulses are equal to number of flip flops. Next one, when scan enable is equal to 0, so data will be capturing operation. Data will be capturing means it will hold, it will store the data. So in capturing operation, so number of clock pulses are required equal to 1. So irrespective of number of flops, so while capturing operation, number of clock pulses is equal to 1. So only one pulse is required. Next one. So this scan chain operation mainly involves in three stages. One is scan in, scan capture, scan out. So data will be in, data will capture and data will be out. So this is the three stages of scan chain operation. So scan chain operation mainly depends upon the scan enable pin. So scan enable is equal to 1, shifting operation. So in this shifting operation, number of clock pulses is equal to number of flip flops, and when scan enable is equal to 0, so it will be capturing operation, number of clock pulses is equal to 1, only one pulse is required respective number of flip flops. So here in this figure you can see blue color line represents functional path. So this will be when scan enable is equal to 0, so scan enable is equal to 0, it will be in functional path. When scan enable is equal to 1, so it is shift chain operation. This is pink line, the pink line represents, so data will go like this, okay. So this is a very important question, generally people will ask in interviews. So next we will see, if you have 10 flops in your design, then how many cycles you need in case of serial and parallel simulation. So sometimes they may ask this question. So 10 flops is in your design, 100 flops in your design, how many clock pulses are required? So if we have 10 flops in our design, so we required, so for loading 10 clock pulses are required, for capturing 1, already we have seen previous question, and unloading data 10 clock pulses, total 21 cycles are required for serial simulation. And parallel simulation, for loading only 1 clock pulse is required. So since all the flops are operate at a time, and capturing data only 1 clock pulse is required, and unloading data is one clock pulse is required. So total 3 clock pulses are required. See here serial simulation depends upon the number of flop count and parallel simulation independent of flop count. So depends on flop count. So irrespective of number of flops in our design, parallel is required only 3 cycles and serial is depends upon the number of flop count. Okay. And next one. So why DFT vectors required less compared to functional vector? Why it's required? So generally DFT is require less patterns or less vector compared to functional vector, right? So in case of two input one output AND gate if you take, so functional verification or functional vectors are required is 8, 2 power 3, 8 vectors are required. For DFT, so number of pins is 2 input 1 output, so 3 vectors are required. So this is one example for comparison between functional and DFT. And why we need to do scan insertion? So what is the benefit of scan insertion? So what is the why we need? So here, to gain controllability and observability of chip design, so we are doing scan insertion. Mainly gain the controllability and observability of our design, so we are doing scan insertion. Okay. So next, what is controllability and what is observability? So controllability, so ability to drive each and every net with either 0 or 1 value is called controllability. Next one, observability, ability to observe the response in output side. Ability to observe the response in output side is called observability. So controllability belongs to input and observability belongs to output side. So these are things you have to remember. Maybe they may ask what is controllability and what is observability. It's important one. Okay. So next one, what is the DFT condition? Then the people will ask, so you are a DFT engineer, what is the conditions? What is the DFT condition? Clock and reset signal should drive from top level. So to gain controllability and observability also we are driving the clock and reset signals from top level. So this is the one condition. And next, what are the types of scan cell design or styles? So we have 3 types of designs, scan cell designs. One is mux-D scan cell, clock scan cell and LSSD scan cell. This means LSSD means level sensitive scan design, So nowadays in modern technology we are following mux-D scan cell, mux-D. So here normal flops is there, we are inserting the mux, right? So that is comes under mux-D scan cell. Okay. Next one, what are the types of scan? So important one, how many types of scans we have? So we have full scan, partial scan and partition scan. So these are the 3 types of scans we have. Full scan means inserting the structure, test structure at a time from top to bottom. So partial scan means bottom up. So this is called, this partial and partition comes under hierarchical model. So these are hierarchical model. So this is flat model. So full scan comes under flat model. Okay. Next one. So what are the types of scan methodology or approaches? Scan methodologies we have. One is top down approach and bottom up approach. So DFT insertion or scan insertion will happen single time. So in bottom up approach, so the scan insertion or DFT insertion will happen different stages, different step by steps will happen. So this is top down is comes under flat model, and this is comes under hierarchical model. So what is full scan, what is partial scan? You can see here. So full scan, all storage elements are converted into scan cells and combinational ATPG is used for test generation. The partial scan, subset of storage elements are converted into scan cells. Sequential ATPG is typically used. So typical sequential ATPG means step by step we will convert scan cells into elements into scan cells, as normal flops into scan flops. Next one, what are the benefits of scan, or what are the scan benefits, or what are the advantages of scan design? So here highly automated process. So highly automated process. So we have a do file. So small changes if you do, you can run the entire design one more time. So next one, highly effective periodical method. So periodical method means step by steps you can do, and highly effective and easy to use. So easy to use. Scan is you can easy to use. If you have decent article commands, we can do this scan benefit, and assured quality will be assured. And next one, so what are the circuit operation types and scan cell modes? So here, so we have before DFT we have a functional operation. So here functional operation we are taking a normal operation. So in this test mode, TM is test mode, scan enable is equal to 0, both are will be 0. And so once so here we are facing the lot of time, and time is more, time requirement time is more, and patterns are more. So so to overcome this functional verification drawbacks, we have a DFT, design for testability. So here we have two methods, two modes, one is shift mode and capture mode. When shift mode and capture mode, test mode will be equal to 1. So test mode equal to 1, then we have to understand that is in DFT mode. And shifting operations can enable equal to 1, and capture operations can enable equal to 0. So very important. So they may ask, so what is the scan enable position while shifting the data? So is equal to 1. So this is something they may ask some cross questions from this table. How do you decide whether we have to use synchronous reset or asynchronous reset? So this will be decided by designer team. So design team will have, so has to decide which one we have to take, either synchronous or asynchronous reset. So DFT team will just make use that the flaps the flaps does not go to the reset state during shift. So during shift the flaps should not reset. So that is how we need to take care. And what is the scan insertion flow? It's very important. So explain the scan insertion flow. So important question for interviews, interview point of view. So this is mainly involves in three phases: setup phase, analysis phase, insertion phase. So what we will do in setup phase? They may ask, explain setup or explain that. In setup phase, we will read all input files. Read operation will happen. Read library file, read get level netlist, and we will read the top model, and also we will set the constraints, and we will also set the clocks, reset offset values, and so we will read operation will happen. And analysis phase, so analysis phase we will check the DRCs. So any DRCs are there, any violations are there, any errors are there, so those things we will check and we will rectify. DRCs like clock controllability DRC, set resetable controllability DRC, bus contention, X source DRCs, and feedback loop DRC. So many DRCs we have: S1, C1, D5, and bus contention, E5. So those DRCs we have to check analysis phase. So once the DRCs are clear, then we will move to the insertion phase. So we will identify the scan equivalent, and we will insert the DFT structure, and we will stitch the scan flops into scan chain, and we will write the scan def file, and ATPG do file, ATPG test file. All these files we will write the after insertion phase. So this is a very important question. Next, what are the inputs and outputs of scan insertion? Very important. So here we have seen, right, previously scan stages. Here, so inputs are required for scan insertion: get level netlist. So we will get from the design team, and library file, do file. So do file is all called script file we will write the script file, and from the after reading the inputs we will assign the we'll check the DRCs and everything will, after that we will write the output. Scan def file, scan inserted netlist we will get, and ATPG test proc file, ATPG do file, and also we can generate the reports like scan cell report, scan chain report, and non-scan cell report also we can generate. We can check the any flops are not converted into scan flops. So these things. So scan cell report and scan chain reports gives the number of chains information, number of flops information, and the clocks information and constraint information, everything you can see in this report file. And so what are the DRCs in scan insertion? Very important. So here mainly these are clock controllability DRC. So S1, C1, S2 like that we will get the DRCs, and set resetable controllability DRCs. So here clock and reset are set. So should be controlled from top level. Suppose if it is not controlled from top level, we will get these DRCs. So these are all are error DRCs. So these two are error DRCs, and these remaining things are warning DRCs. Warning DRCs. So potential race condition DRC, feedback loop DRC, exhaust DRC, bus contention DRC. So here, so bus contention DRCs means one node, one node connected to different buses or different nets. So with different values. So those conditions will get the bus contention DRCs. Exhaust DRC, whenever we have a memories. So memories while doing scan, we need to block the memories. Suppose if we are not blocked, we will get the exhaust DRCs. So these are the DRCs mainly important for interviews. And next one, what information will have test proc file. Test proc file we have to very important. Test proc file we need to check. So here, so basically test proc file will have information about test setup, procedure for test setup, and information about shift, that is procedure for shift, and also procedure for load unload data. So this is about test proc file. And what is scan clock frequency and functional clock frequency in your project? It's very important, this one. So generally people may ask scan clock frequency always less than the functional clock frequency. So when we are doing scan, all the design will be active. So functional only subset of some of the elements only will active. So that's what scan clock frequency is always less than the functional clock frequency. Okay. So functional clock frequency will decide by the design team. So design team will decide. Scan clock frequency will decide by the DFT team, and always scan clock frequency less than the functional clock frequency. Very important. And here example, scan clock frequency 11 megahertz and functional clock frequency 40. This is based on your project. Sometimes it may be 1 hertz, sometimes it may be 10 hertz. So not only 11 hertz. Example I have mentioned here, since we have to show less than functional clock frequency. That's what functional clock frequency, it may be 100 megahertz or 200 megahertz also. So this one is 48 megahertz example. For example, I have taken. So next one, scan clock we can also call slow clock, test clock, shift clock, and functional clock you can also call fast clock, system clock, capture clock. So functional clock always capture clock only. So okay. Next one, how will you take care when there are multiple clocks domains in your project or in your design? See here we need to insert a OCC. OCC means on chip clock controller. Clock controller will control all the clock whenever we have multiple clocks. So OCC will decide. So which clock has to propagate, how many pulses is required, and how many pulses is required. Those things it will decided by the OCC. Okay. So need to make sure lockup latches is there. So here whenever we have a multiple classes, so one is we need to insert a OCC or lockup latches is there, lockup latches is there. So clock scan clock A, scan clock B is there. If suppose if one chain is having two clocks, so in this case we need to have lockup latch. So if planning to mix domains, planning to mix those two clocks, so scan clock A or scan clock B. So do these two clocks if you want to mix in one chain, so we need to add lockup latch. So very important. And next one, domain mixing will do functional clock or scan clocks, very important. So domain mixing means clock mixing. So edge mixing means so different edges of fluff mixing. See, so here domain mixing will do only scan clocks, only scan clocks. So we can also mix other DFT clocks, scan compression clocks or EDT clocks and pipeline clocks. So whether you suppose in the interview may ask question like so can we mix other clocks also? Yes, we can mix scan compression clocks, EDT clocks or pipeline clocks also we can mix, but functional clocks we cannot mix in one scan chain, important. And how to do compression, how to compensate timing, it's very important. So timings always set by the STA engineers, static timing analysis engineers we have. So they will compensate the timings by adding buffers and timings, buffers, lockup latch, those things so they will set, they will fix the timings. So whenever delay engineers will add lockup latch. So the STA engineers are main. So while doing timing simulation, so we have to read the SDC file, SDF file. So it will have it consisting of timings, right. Next one. So what is chain balancing? What will happen if we don't balance the scan chains? Is a very important question. So here dividing equal number of flops in each chain is called chain balancing. Chain balancing. Suppose if we are not balance the scan chains, what will happen? So test time will increase and all scan chains will operate in parallelly and shifting operate at same time. So due to this, if you are not balanced, so chip or design our chip will get burn, our chip will get heat and it will sometimes it goes, it may be burn also, so it will damage. So due to that so due to these reasons we will balance the scan chains. Okay. Next one, what is edge mixing and domain mixing? Important. So edge mixing means keeping both positive edge trigger flaps followed by negative edge trigger flaps in the same scan chain. It's called edge mixing. Combining positive edge and negative edge trigger flaps in one chain is called edge mixing. So edge mixing. Domain mixing means keeping flip flops with different scan clocks. So scan clocks in the same chain. Domain mixing. Okay. So domain mixing also we can call as a clock mixing. So here we can see. So you have in this diagram we have two clocks, clock 1, clock 2. So we are mixing two clocks in one chain with the, what is this, lockup latch. So we are mixing with lockup latch. So lockup latch, why we are mixing lockup latch in this operation? Why it is required? To maintain the delay. So half cycle delay or full cycle, half cycle maximum. So half cycle delay. So we will mix this. We will mix the lockup latch. So whenever we are adding two clocks in one chain, so we need to have lockup latch. So this is about first part of scan insertion. So in next video also we will see some more questions about scan insertion. Thank you.